In a quiet corner of the internet, Andre Karpathy, one of AI's visionary engineers, wonders out loud if we're missing a key piece in how AI learns. At the same time, an experimental AI agent roams endlessly in Minecraft, teaching itself to chop wood, build tools, and survive monsters with no human help. These two breakthroughs on the surface seem unrelated: a thought experiment on AI learning and a video game bot. But together they herald a paradigm shift that could transform industries. Imagine an AI that writes its own rulebook as it learns, becoming smarter and more efficient with each task, and then imagine plugging that into a company. In this documentary, we explore Carpathy's concept of system prompt learning, meet Nvidia's Voyager, the GPT-4-powered Minecraft agent that Carpathy called way ahead of its time, and then envision how these advances could empower LMND, the tech company whose founders are building the first fully autonomous organization to scale in ways previously unthinkable. By the end, you'll see how AI's next frontier might just take LMND from a $1 billion business to $10 billion and beyond, fulfilling its dream of infinite AI scale. Our story begins with a question posed by Andre Karpathy, former head of AI at Tesla and a leading AI researcher. In a recent online thread, Carpathy suggested that today's AI models might be missing a crucial way of learning. He coined it system prompt learning. To understand this, let's first see how AI learns today. The first is pre-training. Like the schooling phase, an LLM reads billions of words across the internet to absorb knowledge. This trains the model's weights, its internal parameters, to capture the statistics of language and facts about the world. The second is fine-tuning, including techniques like supervised learning on specific tasks or reinforcement learning with feedback. Like on-the-job training, the model's weights are tweaked to develop specific skills or align with desired behaviors. Both pre-training and fine-tuning involve changing the model's weights, its brain, which is a bit like a human forming habits or intuitions. But Carpathy points out that human learning isn't just about forming habits. Humans also learn by writing things down, by formulating explicit rules, strategies, or notes to ourselves that we can refer to later. We have an external memory of lessons learned. We jot down, when X happens, try Y, or remember to avoid Z in situation W. In essence, we maintain an ever-growing manual for life. Carpathy argues that current LLMs lack this ability. He says a lot of human problem-solving feels like a change in system prompt, rather than a change in our neural wiring. In AI terms, the system prompt is a guiding instruction or context given to the model. For example, telling a chatbot it is a helpful tutor sets a tone for all its answers. What if an AI could update its own system prompt with lessons it learns, without retraining its weights each time? To make it vivid, Carpathy gives an analogy. LLMs are quite literally like the guy in Memento, except we haven't given them their scratchpad yet. In the film Memento, the protagonist has no short-term memory, so he tattoos notes on his body to remember important facts. Likewise, an LLM today doesn't remember the outcomes of its last task when it moves to the next. It has no notebook or scratchpad where it writes down what it figured out. Every new query starts fresh, as if it never learned from previous mistakes or insights, unless a human fine-tunes it or engineers a prompt to include those lessons. Carpathy's system prompt learning is about giving AI that scratchpad, letting the model itself write down new rules or strategies in its prompt for next time. Instead of only tweaking millions of numeric weights, which is slow, opaque, and data-intensive, the AI would literally edit a text document, its system prompt, that stores what it has learned in plain language or code. Over time, this could become a substantial journal or even a self-written book on how to solve problems, all authored by the AI for the AI. Carpathy notes a few big advantages of this approach. First, data efficiency. Learning via explicit notes or rules can be far more efficient than waiting for gradual parameter updates. He says this knowledge-guided feedback is a higher dimensional feedback channel than a single reward number used in reinforcement learning. In simple terms, it's the difference between giving a detailed review, here's what you did right and wrong and how to improve, versus just a thumbs up or down. An AI writing itself a detailed lesson is much richer feedback than a binary success-fail signal. Second, strategic memory. The AI accumulates a trove of strategies. Next time it faces a challenge, it can skim its journal and recall, last time I saw a puzzle like this, the trick was to do X. This is akin to a human professional drawing on years of written notes and checklists. Third, not just hard-coded by humans. Today, if we discover an LLM consistently messes up a certain task, say counting letters in a word, engineers might hack a fix into the system prompt manually. Carpathy saw this when he peeked at Claude's, an AI by Anthropic, enormous 17,000-word system prompt. It literally had a written instruction for counting letters because the model by itself struggled with that famous count the R's in strawberry trick. To Carpathy, that felt like a crude patch. Rather than engineers hand-holding the AI with such instructions, the AI should learn and write these instructions itself. After all, humans don't need a teacher to follow us around whispering reminders. We learn and write our own mental notes. If system prompt learning works, it could be a new paradigm alongside pre-training and fine-tuning, perhaps as significant a shift as those were. Carpathy muses that a large part of an AI's prompt in the future could be written via system prompt learning, a bit like the LLM writing a book for itself on how to solve problems. It's a powerful image, an AI figuratively turning its experiences into chapters in an ever-expanding guidebook. Of course, Carpathy acknowledges this idea comes with many open questions. How exactly should the AI decide what to write down? How to avoid it scribbling incorrect lessons or clutter? Should those notes eventually be distilled into the model's weights for efficiency? And if so, how? It's uncharted territory, in his words, a lot of details left to figure out. But if solved, the payoff is huge, AI that learns continually in plain language without massive data dumps for retraining. This is a dramatic shift from how we think of machine learning. It moves closer to how humans learn over a lifetime, by accumulating explicit knowledge and heuristics, not just tweaking subconscious connections. It could make AI far more flexible and adaptable, and it sets the stage for something even more interesting. An AI that not only records its strategies, but one that can act and experiment in the world to generate those learnings autonomously. To see what that looks like, let's journey to a place where such an AI already exists in prototype. Get ready for a trip into the pixelated world of Minecraft, where a project called Voyager has given us a glimpse of this future. Picture this. A lone character wakes up in a vast Minecraft world, trees swaying, a square sun rising. No player is controlling this character. Instead, a language model AI, GPT-4, sits behind the scenes, pulling the strings. The AI sees the world state through an API, our character's inventory, nearby terrain, any dangers afoot. There's no preset goal, just like a human dropped into wilderness with an instinct to survive and explore. What happens next is one of the most fascinating experiments in AI in recent memory. This is Voyager, the creation of researchers from Nvidia, Microsoft, Stanford, and others in 2023. Billed as the first LLM-powered embodied lifelong learning agent in Minecraft, Voyager lives up to that mouthful of a description. Let's unpack it in plain terms. Embodied agent. Voyager isn't just a text bot, it's an AI embodied in a game character, meaning it perceives an environment, Minecraft's world, and can act within it, as if it had a virtual body in the game. LLM-powered. At Voyager's heart is GPT-4, a large language model, which the agent uses to reason and write code that controls the character. Lifelong learning. Voyager runs continuously, learning new skills as it goes, without resets or retraining from scratch. It's not just trying to win once, it's trying to get better forever at whatever it might encounter. Now, how does Voyager actually work? The magic is in how it uses GPT-4 as a kind of brain and teacher combined. Voyager has three key mechanisms driving it forward. Automatic curriculum. Voyager doesn't wait for humans to give it missions, it sets its own goals. In any given situation, it asks GPT-4 to suggest an objective that would be reasonable to pursue next. For example, if it finds itself with a fishing rod in inventory and a river nearby, GPT-4 might propose, "Let's go fishing to gain some experience." If it's night and monsters loom, the goal might be build a shelter or craft a sword. This creates an automatic curriculum, a self-driven lesson plan, where Voyager always has something to strive for, suited to its current context. It's like a student that not only learns the material, but also figures out what to learn next on its own, always pushing the frontier of its knowledge. Skill library. When Voyager attempts a task, it does so by generating Python code in a JavaScript API for Minecraft to execute actions in the game. At first, it might stumble. Suppose the goal is collect wood and build a crafting table. GPT-4 writes some code. Voyager tries it, maybe it fails or errors out. Crucially, Voyager can read the error messages or see that nothing happened, and then GPT-4 will debug and refine the code. Once the code finally works and the task is done, wood collected, table built, Voyager saves that code in an ever-growing skill library. This library is essentially memory, a repository of skills in code form that it has mastered, like functions it can call later. So next time when it needs to build a crafting table or fight a zombie or bake a cake, it can retrieve the code for that skill instead of starting from scratch. Over time, the skill library becomes very rich, a toolbox for just about any situation, accumulated by experience. The researchers note these skills are interpretable, it's code we can read, and compositional. They can be combined for more complex tasks. It's as if Voyager is writing its own cookbook of recipes for different challenges in Minecraft. Iterative prompting with feedback. How does Voyager improve when it fails? This is where it truly embodies Carpathy's idea of learning from explicit knowledge. Voyager uses an iterative prompting loop. After each action attempt, it feeds GPT-4 with the outcome, error messages, or a description of what happened. GPT-4 then reasons about this feedback. The code didn't run because I got stuck underwater and drowned. Perhaps I should have the agent swim up for air periodically. It then revises the plan or code accordingly. This loop repeats until success or until GPT-4 determines a different approach is needed. Essentially, Voyager is learning from trial and error in real time, and crucially, writing down the successful approach into the skill library as above. No gradient descent, no parameter updates, just pure in-context learning. The researchers highlight that Voyager manages to do all this without any fine-tuning of GPT-4's parameters. GPT-4 remains a fixed model. Voyager's growing prowess comes entirely from the skills and strategies it accumulates in its prompt and memory. This is precisely that no-gradient architecture vision. The LLM, GPT-4, acts like a prefrontal cortex, orchestrating actions via code and learning via new prompt content rather than weight updates. So, what did Voyager achieve with this setup? The results were groundbreaking. Over many hours of autonomous play, Voyager became arguably the most capable Minecraft bot to date. It learned to mine iron and diamonds, farm crops, fight hostile mobs, build furnaces, effectively progressing through the tech tree of Minecraft much faster than any previous agent. According to the team's report, Voyager obtained 3.3 times more unique items, traveled 2.3 times farther, and unlocked key advancements up to 15 times faster than prior state-of-the-art agents. In the context of Minecraft, that's like leaping from the Stone Age to the Iron Age in a fraction of the time. Voyager discovers new Minecraft items and skills continually by self-driven exploration, significantly outperforming the baselines. These numbers aren't just video game high scores, they're a proof of concept that AI can learn continually in an open-ended environment, improving itself with minimal human intervention. It's exactly what Carpathy was talking about. Instead of engineers fine-tuning the AI or hard-coding tricks, Voyager learned by playing and writing its own tricks into its memory. Little wonder that when Carpathy saw this, he lauded Voyager as being way ahead of its time. It was a glimpse of AI's future before most realized it. The Voyager project also illustrated some fascinating points about AI development. It showcased the power of letting a model be both student and teacher. Voyager used GPT-4 to generate ideas and also to critique and refine them. This self-reflective loop is like having an inner coach. It emphasized lifelong learning in a way rarely seen before. Traditional AI agents often reset after completing a task or episode. Voyager never resets, it just keeps accumulating abilities. This helps avoid what researchers call catastrophic forgetting, where learning new things makes the AI forget old ones. Because it continually practices and refers back to its skill library, it was highly interpretable. Anyone could open Voyager's skill library and see exactly what it learned, since its code and textual notes. That's a far cry from trying to decipher millions of neural weights. For safety and development, this transparency is a huge bonus. Given all this, why isn't every AI agent using Voyager's approach now? This is where the ahead of its time bit comes in, not just as praise, but as a literal explanation. Voyager is a complex system, and it was debuted in a very specific domain, Minecraft. Minecraft is an ideal sandbox, literally and figuratively, because it's open-ended and reasonably accessible to an API. But outside of a game environment, setting up a similar loop is more challenging. For one, Voyager leans heavily on GPT-4, which, running continuously, is computationally expensive. Few applications can justify having a large and sometimes slow language model think through every little step in real time. at least with current technology and costs. Additionally, many real-world tasks don't have a simulator as forgiving as Minecraft. In Minecraft, a mistake might cost your agent a few in-game lives or items. In the real world or a high-stakes business environment, mistakes have consequences, money lost, safety risks, etc. So letting an agent try, fail, and learn on the fly requires careful constraints or simulations. Moreover, Voyager's brilliance comes from stitching together several advanced techniques: code generation, feedback loops, self-curation of goals. It's cutting-edge research with many moving parts. The wider AI community is still digesting these ideas. As of now, many companies are just getting comfortable with using static LLMs, for example, using a frozen GPT-4 to answer questions or generate text. The notion of an autonomous, self-improving agent is a leap that requires rethinking AI architecture from the ground up. In short, Voyager hasn't been widely adopted yet because it's early, and it pushes the envelope of what we know how to deploy robustly. But make no mistake, it has lit a path forward. It demonstrated that an AI agent can accumulate knowledge internally without constant human fine-tuning and adapt to new challenges by building on past skills. Carpathy's system prompt learning lives in Voyager's DNA. Voyager effectively learns new system prompt content, skills, instructions as it goes, rather than waiting for a gradient descent update. It's a cousin of the paradigm Carpathy described. This brings us to the third act of our story. We've seen the theory, AI writing its own book of wisdom, and we've seen a practical example, an agent that masters a complex world by itself. Now, it's time to leap from Minecraft to the boardroom, from open-ended play to the very real world of insurance. How can these concepts transform an AI-first company like Lemonade? Lemonade, the company that got its start selling renters insurance to urban millennials through a slick app, might not immediately remind you of cutting-edge AI research. But look under the hood, and Lemonade is as much a tech company as it is an insurer. In fact, Lemonade has often touted itself as a vertically integrated AI-driven insurer built from scratch. Unlike traditional insurance carriers that bolt on third-party software or rely on armies of human brokers and adjusters, Lemonade built its own end-to-end platform. It owns the customer app, the policy management system, the claims processing pipeline. All of it. This vertical integration means Lemonade has complete control over its data and processes, an ideal playground for deploying advanced AI. At Lemonade's 2024 Investor Day, poignantly titled The Next 10X, the company's leadership made it clear that AI is front and center in their growth plan. CEO Daniel Schreiber and his team outlined how they plan to grow the business tenfold, from about $1 billion in premiums to $10 billion. A huge part of that story, leveraging AI to achieve what COO Adina Eckstein called infinite scale. By infinite scale, they mean breaking the traditional link between growing your business and growing your costs. In a typical insurer, if you double your customers, you might need to double your customer support staff, claims adjusters, underwriters, and so on. Lemonade's vision is different. Many functions are handled by AI and automation, so serving more customers adds relatively little incremental cost. In their words, AI enables infinite scale. Software handles an expanding workload with minimal human intervention. This isn't just wishful thinking. Lemonade showcased real AI bots in action at that Investor Day, demonstrating how claims get processed and customers get served with hardly any human in the loop. They even bragged about internal automation wins. For instance, 80% of the company's financial reports are generated automatically by AI, and 95% of certain internal requests are handled through automated processes. That's the back office running on autopilot. And on the front end, Lemonade's AI chatbot Maya sells policies, while another AI persona, Jim, handles claims in seconds. In one famous example, Lemonade's claims AI approved and paid a claim in 3 seconds. Try getting a human to even read the claim that fast. This is the kind of efficiency that has allowed Lemonade to service over 2.5 million customers with a lean team. But as impressive as this is, Lemonade's current AI is still largely based on predefined models and rules. It uses machine learning to detect fraud or assess risk, yes, but it's not yet the self-learning, autonomous agent we've been discussing. That's where our story's first 2 acts come in. Imagine Lemonade upgrading its AI stack with system prompt learning and Voyager-like agents. What could that look like? Let's paint a picture of Lemonade's possible future. Call it Lemonade 2.0, an AI-first insurer that's truly autonomous. Crucially, with system prompt learning, each claim that the AI handles becomes a learning experience. Suppose someone tries a novel fraud tactic that slips through. The AI could realize later, when an audit discovers the fraud, that it missed something. It would then write a note to itself in its system prompt. When a claim involves X scenario, verify Y to catch fraud. Essentially, it builds its own fraud detection checklist as these cases occur. Over time, this AI adjuster has an encyclopedic memory of scams, customer behavior patterns, and optimal ways to adjudicate claims. It's like a veteran human adjuster with 30 years of experience. Except it gained all that in a matter of months by learning from every single claim across millions of customers. The result? Near zero processing time, superhuman fraud detection, and consistent decisions. Customers get paid faster, fraudulent claims get caught earlier, and Lemonade saves money. It's worth noting that Lemonade already has a lower fraud loss rate than industry averages in some segments, thanks to AI flagging suspicious cases. Future AI could push this even further, effectively vaccinating the company against many fraud vectors. We can even imagine Lemonade's AI platform as an ensemble of agents, each specialized but sharing knowledge. A claims agent, a pricing agent, a service agent, etc., all plugged into a central knowledge repository, the global system prompt. If one agent learns something, say a new scam, it updates the repository, and all agents now know to watch for it. This is like having separate departments in a company, but instead of holding meetings, they update a common database, which they all read from diligently. Corporate knowledge isn't trapped in silos, it's instantly global. That's only possible because Lemonade's tech is unified, vertically integrated, and the AI can interface with all of it. A legacy insurer with patchwork systems couldn't easily do this. Lemonade can. Insurance is famously a grudge purchase. Nobody enjoys buying it, and certainly nobody enjoys filing claims, often a stressful time. If AI can make the experience smoother, instant answers, lightning-fast claims, Lemonade could win on customer satisfaction. Happier customers tell their friends or at least stick around, improving retention and lifetime value. Lemonade has always marketed itself as the lovable, pink logo insurance that behaves differently. AI superpowers would back that up by delivering delightful service at scale. In this three-act saga, we saw how AI is learning to learn. Andre Karpathy's idea of system prompt learning highlights a paradigm shift. AI that doesn't just passively rely on big offline training sessions, but actively builds its own knowledge in real time. Then we met Voyager, the embodiment of that idea in a blocky video game world. An AI agent that iteratively writes its own code, sets its own goals, and continuously improves. Voyager gave us a concrete example where AI achieved feats, 3 times more items, 15 times faster progress, by doing something profoundly human, learning from experience and keeping a record of lessons learned. Finally, we brought these threads to Lemonade, envisioning an insurer that runs on AI autopilot, AI handling claims, refining pricing, detecting fraud, and delighting customers all in a unified loop of improvement. Lemonade's leadership already speaks of AI enabling infinite scale, and we explored exactly how that could play out. It's a future where Lemonade's AI accumulates strategies to become ever more efficient and effective at compounding speeds that, at velocity, creates an ever-growing moat. AI is entering a new phase, one where it can learn like a human and act with superhuman speed. Companies that harness this will redefine productivity. Lemonade's quest for infinite scale is just one example, but a powerful one, of what an AI-first company could achieve. It's a vision of machines that learn from experience, businesses that run on autonomous intelligence, and customers who benefit from faster, smarter services. In the end, what we're really witnessing is the early chapter of AI writing its own book in the history of technology. And that's a story worth following, and one we'll be watching closely. Thank you for joining us in this exploration of AI's cutting edge and Lemonade's bold vision. If you learned something new and exciting today, don't forget to like this video and subscribe for more deep dives. The age of autonomous enterprises is just beginning. Stay tuned because the journey from Minecraft to Wall Street has only just begun.